Okay, so now you've seen what the problem is with having many dimensions, especially when you want to use machine learning. The more dimensions you have, the more training data you need in general. And you've seen a somewhat oversimplified way of reducing the number of dimensions. We increased it rapidly on the worksheet to just 2 dimensions. What's more realistically done in practice is in natural language processing, you apply a so-called stemming algorithm, which reduces words to their stem. So for example, both the plural form and the singular form will be reduced to the same stem. In this case, it's student. And this already reduces dimensions a lot because you don't have all these variations in words. Another very common technique is called stop word removal. So stop words are words that appear in pretty much any document. For example, articles, the, in, an, a. And if you do TF-IDF scaling, you know that these are essentially useless because they appear everywhere. You can see that the document frequency is equal to the number of documents, and they would just cancel each other out. So there are predefined lists for many languages of stop words that we can just remove. And this again reduces the dimensions minus the number of words in this stop word list. And it's just 2 steps in a natural language processing pipeline. So especially in the next couple of weeks, we'll look more into natural language processing. And the idea there is that you can apply different kinds of algorithms step by step in the pipeline. So you start out from the individual characters that come in your chatbot, for example, or another application. And then the first step would be to group these individual characters together to so-called tokens. For example, individual words or numbers and so on. And this is very often done with regular expressions, this splitting out of words into tokens. Then a step that's often being done is finding out what kind of word is it. Is it an adjective? Is it a noun? Is it a verb? And this helps, for example, when we later want to identify the subject in a sentence. For example, we would need the subject to search for it in a Sparkle query. We can find out which word is the subject in there and extract this and plug it into a Sparkle query, for example. So this is done with a step called part of speech tagging. We want to find out what is the part of speech, like noun, verb, adjective, adverb, for each token that we generated from the characters. And then there are more and more steps that build on top of this. For example, finding out the syntactic structure of the sentence. What is the main verb, subject, object, and so on in the sentence. And again, this helps, for example, in answering questions that come into a chatbot. You can detect relationships between these words, and it's also possible to at least partially generate knowledge bases based on the automatic analysis. So there are people that do research on automatic knowledge base construction from natural language documents. So here you can see a number of applications that match with the analysis step. So chatbots you find in a couple of these steps because you've seen that we can build very simple chatbots using just regular expressions. We can also build more sophisticated chatbots that do a more detailed analysis of the input sentences. For other AI applications, other NLP applications, you need more advanced steps in this NLP pipeline. When it comes to more complex question answering, where we need a knowledge base, we also need a more advanced analysis of the text. But before we go to these later steps, let's look a bit more into the first steps in the pipeline. So the very first task is this tokenization, which you've seen here. We have individual characters and want to group them together into tokens. And you might think, Well, what's the big deal? That's the easiest thing ever. So there are a number of tools, and they are called tokenizers. Typically, they work using regular expressions, and in scikit-learn, there is a tokenizer included that you can use for various applications. Why this is not easy, you can see when you look into documents from different domains. For example, if you look into biomedical documents, it's not easy to find out what words, what letters should be split into a token. Now, if you have something like this here, a 1,4 beta-xylanase 2, this is a protein, then where do you split this? If you want to be able to identify this exact protein, you can't just say, okay, let's split it at the hyphen, or let's make this here into a number. And what do we do with the beta here? And what about the 2 there? So it can be very complicated to decide where does a token begin and end in complex expressions like this. And that's not even a complicated case. You have things like this here, the N-formyl L-methionyl L-lysyl L-phenylalanine, or you have some crazy stuff like the one shown here, which I'm not even trying to read. So this whole thing here is something that belongs to a family of compounds. So now if you split this up in different places, all the later analysis steps that try to figure out what kind of chemical compound this is might not get the right answer. So you learned your first lesson in NLP, even the things that look like they are simple, as soon as you go into real life and you deal with real world documents, even the simplest steps can become really complicated. And because this is done in a pipeline fashion, if you make a mistake early on, the mistake is going to propagate throughout the whole pipeline and mess up your results that you get out at the end. So biomedical documents are just one domain. It happens to be really complicated, but you can also see what happens when you work on software documents with source code, on mathematical documents with formulas, maybe on other documents that have lots of tables. So tokenization sounds like it's easy, but if you apply it in a real world fashion, it gets complicated quickly. The next step that you do is this part of speech tagging. So you have to know what it is, assigning a part of speech tag to each token. So we have the token from the previous step, and now there's another algorithm typically done using machine learning that assigns a token to each word. So the would be a determiner, big would be an adjective, dog would be a noun. And we'll see in the lab there are these tags. They come from so-called tag sets that are, there are a few ones that are typically used in practice, and you can look them up, what these tags mean. So this is a step that can be done pretty reliably. It depends a bit on the domain. If you switch between, let's say, biology to mathematics to novels or blog posts, the performance is going to change. But overall, this can be done reliably, and there are a lot of libraries available. How these algorithms work, we're not really talking about in detail. Again, it's done using machine learning. If you take a natural language processing course, you're learning how to do this in detail, how the algorithm works, and so on. Here in this course, we're just going to use the libraries that are available. For example, for Python, there's NLTK or spaCy. The next step is this parsing, finding out what the grammatical structure of a sentence is. So here, for example, you see the sentence, the chef cooks the soup. So the top is the sentence, and then we find out what the noun phrase and the verb phrase in the sentence is. Noun phrase is the chef, and the verb phrase is the verb plus another noun phrase. And this is one way of representing the grammatical structure of a sentence. And then in our application example of a chatbot, we could use this to extract information about the verb or the noun or the object or the subject, extract it from the sentence, and, for example, plug it into variables in a SPARQL query. To see how this works in practice, you can use an online tool, which is here on the worksheet, the task number 5. Try this out, and then I'll see you back in the next lecture part.